Hi everyone, today we're going to have a look at some voltage reference standards modules here, which you'll see quite often on websites like eBay, and they vary in price from around £10 per unit to around £65 or even more in some cases, depending on the type. I have three here which you might be interested to have a look at. I'll look at each one in turn and I'll discuss the technology behind them and the pros and cons of these three voltage reference standards. They're quite useful for checking the calibration of your test meter, and in a lot of cases when you get them you'll see that it comes with a calibration reference giving you the voltages that they've specified when they've manufactured the unit. Okay, so let's have now a look at each of these items. Right, here you can see the three items. This one here is the cheapest of the three. It's using a analog devices IC, the AD584L, although you can get a version of this with the AD584K, which is a slightly lower specification. And similar with the one in the middle there, that's also using the AD584. In this case it's the 584L, but again it's also available with the K version. Both of these two modules tend to come from either China or Hong Kong, and you see quite a number of sellers offering these on eBay. Also, both these two units can give you reference voltages ranging from 2.5 up to 10 volts in 4 steps. So that's 2.5 volts, 5 volts, 7.5 volts and 10 volts as a reference standard. The unit on the right is a 10 volt reference standard only. This one tends to use either a Texas Instrument IC or a linear technology IC, and it's just in a 10 volt version, but these tend to be more accurate than the previous two here. As a result of that, the one here on the right is by far the most expensive, and that can vary in price from around £40 to £65 depending on the tolerance. Well, let's have a look at each of these items in turn, and I'll start with the simplest one, this one here on the left. Right, here's a closer look at that unit. Quite simple. The main component there is the reference voltage IC there, which is the analog devices chip, and the only other components on the board on this side is a small 0.1 microfarad capacitor, an LED with its source resistor of 5.1K, and these two connections here are your output connections, which you can actually just slide in your test leads or any other pins. The two switches here, the top switch is simply the on-off switch, and the other switch there is a slider switch which switches through the 4 ranges from 2.5 up to the 10 volt range. The input supply to the board is at this side here. You can see the wires connected on the plus and minus, and the nominal voltage input recommended for this is probably 14.5, 15 volts, although it will work down at 12 volts, but I would strongly recommend that you use probably 15 volts for this item, and I'll show you the results of that shortly. On the reverse side of the module we have a capacitor which simply across the input supply voltage, that's just a 220 microfarad low voltage capacitor, just filtering out any noise on the input supply, and that's basically it. So that's the first module. It comes in a silver package, and they give you their calibrated references for this particular unit, and the reason behind this is that this particular chip does vary slightly from one to another, and what they've done here, they've measured it with their test equipment at source, and for each of the ranges 2.5, 5 volts, 7.5 and 10 volts, they actually give a reading of what they read using an Agilent meter which was calibrated. You'll find that these will vary from different modules if you buy several of these. I actually purchased 2 items from this company, and you'll see that the second one here has different reference voltages that they've measured. But the good thing is they give you the calibrated reference for each unit, so that's quite a nice touch. Okay, here we have the unit now connected to the power supply here. At the moment I have the power supply on 12 volts, and on this side you can see the reading on the Keithley 2000 meter here. It's reading 9.99952. Now that's when we have an input voltage of 12 volts, but this particular IC on this module, the AD584, has quite a wide input voltage option on this, anything up to 40 volts, and the nominal voltage is probably operating at a best voltage around about 15 to 17 volts. So what I will do now, I will input into the unit, I'll increment it by a volt at a time. At the moment it's on 12 volts. You can see the reading there on the meter. I'll now put in 13 volts. There again you can see the reading. It's the last 2 digits is 54, 5453. I'll go up to 14 volts on the input. It's crept up a little bit there now, 5655, the last 2 digits there. That's on 14, so I go now to 15 volts. Again it's creeped up slightly, now to 5.6, 5.7. So we now do 16 volts. Last 2 digits now running at 5.7, 5.8. And then 17 volts, we'll try in the input. Last 2 digits are now around 5.9. And I'll put in 18 volts. And with 18 volts on the input of this module, we're getting exactly 9.99960 of a volt. Now according to the specification on the calibration certificate on the bag that it came in, they're stating 9.99968, so the last digit is out by 8. So I think the ideal voltage for the input is probably around 15 volts. And bear in mind that when you use these voltage reference sources, it does take a little while for the IC to warm up, and the voltage does vary on warm up. I've now got the meter now set back at, I've now got the power supply set back at 15 volts on the input. I'll now switch the mode switch to the 7.5 volt range, and there it's showing me a reference of 7.49876, and according to what they sent me on the packaging, they said it should read 7.49886. So there's a little bit of a difference there on the last 2 digits, but again the module hasn't yet fully warmed up. We'll switch on to the 5 volt range. There's the 5 volt range, reading virtually spot on 5 volts, 5.00032. According to the specification on the packaging, it said it was 5.00042. So again, just a slight differences, but it could be that my Keithley meter here is just a fraction out of calibration. And then finally on the 2.5 volt range, it's reading 2.49910. According to their reference on the packaging, it should have read 249918. So again, it's just the last digit is out by 8. It's just a tiny amount, and again, as I said, it could be that my Keithley meter maybe it's just a fraction out of calibration, so this unit may be okay. So it's quite a nice little unit. This is the least expensive of the three that I just showed you. These you can get these for around about £9-ish on eBay. Okay, well, we'll have a look at the circuit of that, because it is so simple you could probably build one yourself. So let's just have a look at the circuit diagram for that. Okay, well, there you have the circuit. There's the IC, the AD584. This particular chip you can get in two packages. You either get it in an 8-pin DIL package, dual inline, or as we've seen on the module a moment ago, they're using the TO99 8-pin package, the round package. The input supply to the IC is going on to pin 8 through the on-off switch there. I strongly recommend 15 volts as the input supply, and in fact when you look at the technical specification for the chip, I think it does also recommend 15 volts. On the input they also put the LED, so you've got an indication when the thing is switched on, so just a little red LED and a 5.1k resistor. And then they've strapped a capacitor of 220 microfarads on the input supply, just to smooth out any sort of glitches there, any sort of spikes you might get or any interference. The little capacitor between pin 6 and pin 7 is like an optional which you can choose. They recommend that if you add anything between a 0.01 and a 0.1 microfarad capacitor between those two pins, it will reduce the effects of noise. So probably a good idea to put that capacitor in. They're using a 0.1 on this module. The earth for the chip is pin 4, and the main output pin for the chip is pin 1. So what you've got coming out of pin 1 normally is your 10 volts. You've got your 10 volts reference there, but there's two other pins here, pin 2 and 3, and depending on how you switch these pins, it'll determine what the output voltage will be. So if you just use pin 1 on its own, you get 10 volts. If you were to put a shorting link across pin 1 and pin 2 there, you'd get 5 volts. If you put a short between pin 1 and pin 3, you'd get 2.5 volts on the output. If you put a short between pin 2 and pin 3, you get 7.5 volts on the output. And with none of them connected, that's open, you get the normal 10 volts coming out. This is achieved by a potential divider ladder, which is actually inside the chip. That's a precision resistor ladder inside the chip. So you're just switching out resistance in the chip when you put these shorts across. I've shown it here as the connections on a slider switch, so you have to slide a contact there or there or there or there. The chart at the bottom is just showing you the different types of this IC that are available. The letter after the number can either be a J, a K, L, S or T, and depending on the type that you select, the tolerance varies. And this particular module that I've demonstrated, they're using the L type, so they're using an AD584L, which is the best specification. On the 10 volt range you get an error voltage of plus or minus 5 millivolts. On the 7.5 volt range it's plus minus 4 millivolts. On the 5 volt it's plus or minus 3 millivolts, and on the 2.5 volt range it's plus or minus 2.5 millivolts. So you can quite clearly see that that is the best type for this chip in terms of maintaining that reference voltage. And there you got the K version. You'll find also the cost between these varieties varies tremendously. If you choose the cheapest one, the J, you have a much wider tolerance error on the output voltages. The last two types here, the S and the T, are more or less for military or very high precision requirements. and that's mainly because the temperature, operating temperature on these two can go between minus 55 degrees C to plus 125 degrees C, whereas the normal chips here, the J, K and L, they'll operate between 0 degrees C and 70 degrees C, so that's what you'll normally see probably. The overall line regulation of this circuit, once you've got the voltage coming on the output here, it'll maintain that voltage at an accuracy of, I think it's 0.002, plus or minus 0.0002%. So quite stable once you've got your output supply voltage there. So it's a nice little circuit. As I said earlier, you could probably build one of these yourself simply by buying the chip, and you've just got a few components there and a switch. The only thing is, this particular module that came from China was only costing less than £10, and you may find you're having to pay something around that just to buy the chip, especially if you're choosing the L version of that chip. Okay, so there we have the first module. Right, we'll take a look at the second module here. It's housed in a nice clear plastic case, which looks like it's been laser cut, this plastic, very nicely done. The two banana sockets on the front there, and a little push button switch there beneath the plastic, where they've trimmed out the plastic case around it, so you can just press on top of the plastic there to operate the unit. Very nice. And on that side there we've got the input jack for a plus 5 volts DC to charge the lithium polymer battery. Across the bottom there you've got the voltage indications there from 2.5, 5, 7.5 and 10, and behind those you have red LEDs that come on depending on what voltage range you're on. I'll just turn the module round, because on the back side they've actually put the calibration readings that they took when they tested it after manufacture. Okay, here you can see the calibration readings that they took after they put this unit together, and for each of the ranges there they're given the actual reading that they got using a Agilent 34401A, which was a meter that was calibrated. So the calibrated readings they were giving here for the 2.5 volt range, they're giving 2.49868. For the 5 volt range they're giving 4.99906, and the 7.5 volt range is 7.49957, and finally the 10 volt range is 9.493. And they give you a date there when this unit was calibrated. On this particular one it's in 2013. Right, I've got the unit connected to the Keithley Multimeter you can see there above. At the moment the unit is switched off, and to turn the unit on you press the little tactile button there you can see in the middle. You hold it in until the LED comes on, so you press it in, hold it, there you see. Once one of the LEDs comes on you let go. The first LED to come on is the one for the 2.5 volt range, and it's reading on the meter you see 2.49861, and on the back they indicate it should read 2.49868. So again I think it's pretty accurate, and again you know, you've got to bear in mind that the meter I'm using may be a fraction out of calibration or so. If I press the button one more time it goes to the 5 volt range. That's reading 4.99910, and they're suggesting it should be 4.99906. Again, it's more or less spot on. Press it one more time, goes to the 7.5 volt range, and that's reading 7.49973, and they're suggesting it should be 7.49957. And then finally the 10 volt range, there indicate it's reading at the moment 9.99955, and they're suggesting 9.99956. 99993. So they have the unit displaying the voltage settings there. I'll switch the unit off now, and then I'll just take the top cover off and just have a closer look inside. Okay, there you have a clearer view. You can see some of the elements to the module here. There's the chip, the voltage reference chip there, and the 4 LEDs you can see at the back, and there's the push button, the tactile switch there, which is the range selection switch. This area of the board you have a DC to DC booster circuit to boost the 3.7 volts up to higher voltage of around 15 volts to feed the reference IC. This area of the board is to do with the charger and charger protection circuit for the lithium polymer battery. There's the two chips there to do with the lithium polymer charger. That's the input jack socket there for inputting 5 volts to charge the battery, and that LED there is a blue LED that is an indication when the unit is charging. It lights up blue. When it's finished charging, it goes out. And then in this part of the board here you've got another logic IC, but for some reason they've scraped off the information off the top of that, so we don't actually know what that chip is. It's some sort of logic chip, or it could even be a small microchip that's got the software in to control the unit. I've just lifted the module away a bit more so you can see the lithium polymer battery, which is stuck on the bottom of the case there. I think what we'll do now, we'll have a little look at the schematic of what the circuit is for this particular module. Okay, here we can see a block diagram of the schematic for this module. I've tried to indicate here the main blocks in there that are addition to what we saw earlier. There's the chip, the AD584L, the reference IC, and on the input side here, the battery there, you have a 3.7 volt lithium polymer battery. You have a LiPo charger circuit there, which is using the 8205A and the DW01 chipset there for the charger, and you have a socket there which is for the 5 volt DC in to feed the charger. There's a blue LED which is also connected to the charger, which indicates that the unit is charging and goes out when the battery is fully charged. The output voltage from this then goes to a DC to DC boost converter, which is using an MC34060, which is a pulse width modulator IC and control circuitry, and that boosts the voltage up from the 3.7 volts up to around 15 volts to feed to the reference IC. The heart of the unit in terms of control is some logic circuit there. Unfortunately they wiped away any identification on top of that chip, so we don't exactly know what chip it is. It could be just a logic IC that they're using, or more likely it may be a small microchip which they've programmed to do this particular function for this switching function for this particular reference module. The reason I'm saying that is that these outputs coming from this logic IC feeding 4 transistors that feed the red LEDs that indicate which voltage range you're on. Also coming from that you've got the push button, which is the selection button on the ranges. That's also going to the logic IC circuitry there as well. So it's clearly that's what's controlling the unit in terms of switching between the ranges. And then the output voltage for the reference is coming from pin 1 of the AD584L and earth. So there you've got coming out your reference voltage, depending on what range you've selected. So that's a simplified sort of block of the circuit that's used on this particular module. As I said earlier, this one, because of the complexity, it actually costs a little bit more than the previous one, but even so, on eBay you can buy these for around about £14–15, and it's complete with the lithium battery and the case and everything, so it's not a bad investment really, and the accuracy is pretty good. Well, it's the accuracy of the chip really, which is the L version, the same as what I illustrated on the other board. Here's a typical listing of that module on eBay using the AD584 chip. You'll actually find there's quite a few supplies of this on eBay, either from Hong Kong or China. The price varies slightly, but it's round about £14-ish. Okay, here's the third of the units we were looking at. This is the most expensive one and the most accurate of the three. This particular one gives a fixed 10 volts DC out with an accuracy of plus or minus 0.0006%. That means it's 6 parts per million, so it's very, very accurate. And this has actually been calibrated before delivery, and the sort of calibration equipment they were using were fluke calibration equipment. So I would imagine that it's been done to a very, very precise level. Now, the only problem I had with this is identifying which were the inputs and which were the output sockets. They're not marked on top, although when you reverse the unit round, you do have some instructions on the back. I'll just read them out. It says DC voltage standard. It does say that the input voltage range can be between 12 volts and 35 volts DC, and it says the optimum they recommend is 14.5 volts DC, and the output is a fixed 10 volts. It also gives you there what the calibration error was when they did this, and it's again plus or minus 0.306% at 75 degrees Fahrenheit. Now, it does say there that the input terminals are on the left and the output are on the right. But when I turn the unit round, it's a bit difficult to say which is the left and which is the right, because I could have it that way around, or I could turn it that way around. And in fact, the correct way is, if I hold it that way, with the green dot at the bottom near the black terminals there, you see, that is the correct way to look at it, and therefore the terminals on the right here, I'm just indicating with my thumb, are the output terminals, and the terminals here on the other side are the input terminals. Right, what we'll do now, we'll plug the unit in, put some power to it. I'll put 14.5 volts to it, and we'll just see what the voltage reference is coming out. There we have the unit plugged in now. I've got the output connected to my Keithley 2000 multimeter there, and I have the power going into the inputs here from this power supply. I will program in 14.5 volts DC, which is what they recommend, and then we'll look at the output there, see what the output is. And there we're getting a reading of 10.0003 of a volt, dropping down to 2. Bear in mind, I've only just plugged the unit in, so you may find that it needs to warm up a little bit to get the most accurate. In fact, I would probably recommend you have it on for at least half an hour to let it settle down. What I'll try now is I'll just lower that voltage down to 12, because they do say that it will work from anything between 12 and 35 volts. So let's put in 12 volts. And as you see there, the output is reading 10.00018. If I were to put in, let's say, 20 volts, output's reading now 10.00013. I'll go back now to 14.5, which is what they recommend. Yeah, it doesn't seem to make a great deal depending on what input voltage you have within the range that they stipulate, but they do recommend 14.5 as the voltage to use. Right, I've just taken the unit out of its case and just to ease it off slightly. The actual little printed circuit board there is also screwed down into the base of the case, so I had to release them as well. It's very tight actually. There's the chip which is socketed, and we have 3 resistors, a diode, a capacitor and a small trim pot there for calibration. The IC that's in here, interestingly, is the linear instruments IC, which is LT1021, whereas when I saw the unit advertised on eBay, it referred to the chip that they used as being the Texas Instruments REF102. So it's not the same chip as what they advertised, although it's a similar IC in terms of accuracy to the Texas IC. But I'll just have a look at that and just compare the two shortly. Okay, so very simple circuit, not a great deal in there really. This is certainly something you could build yourself. The only difficulty you would have would be calibrating it, and that's obviously being calibrated after it was assembled, and unless you actually have the calibration equipment to hand, such as a Fluke 732A, and then you find it difficult to calibrate this unit accurately. So I think here what you're paying for is not so much the components that we have in the module. You're actually paying for it being calibrated once it's been put together. So it's calibrated to a high standard, but the unit itself, there's not a great deal inside. Let's see if we can make out the circuit for this and have a quick look at that. Here we have the circuit of that module. It's quite a simple circuit really. There's the reference IC. It can be one of two types, either the REF102C, which is a Texas Instrument IC, or a LT1021C, which is a Linear Technology IC. Both of these chips deliver a 10 volt reference out, very high stability. The only difference is that the maximum error on the REF102C chip is plus or minus 0.0025 of a volt, whereas on the LT1021C chip it's plus or minus 0.005 of a volt. Also, the maximum drift per degree centigrade is 2.5 parts per million for the first one and 5 parts per million maximum for the second one, although in the technical specification it does say that this particular chip, the LT1021C, typically that figure would be 2 parts per million. So there's very little difference between the two, but I suspect that the Texas one, the REF102C, is slightly better, and it's actually a little bit more expensive. Okay, as far as the circuit's concerned, quite straightforward. The input voltage goes on pin 2. Interestingly, they've put a small diode on the negative line to give some sort of protection in the event of you trying to connect the voltage in the reverse way, and there's a little filter capacitor there on the input voltage terminal there, a 0.1 microfarad capacitor. The input can take anything from 12 volts to 35 volts, as I said earlier, but they recommend you use a 14.5 volt supply for the input. On the output you have a trim circuitry here. You can just take the output from pin 6 and get 10 volts out, but you can actually trim this IC to trim out any errors, and that's what's happened with this particular module. After it's been built, they actually trim out the errors, and that's a little trim circuit there from pin 5. A 75k resistor goes into a 2k pot, so very little movement there on the trim, and 220k resistors either side, and they would trim that then for exactly 10 volts on the output. So the trick there would be connect the output of this on some calibration equipment and then adjust the preset pot there to get exactly 10 volts out. So they're actually improving on the standard reference voltage coming out without any trim here. That's the standard reference voltage that would come out of this chip. By putting the trim circuit on, you can improve that dramatically. And when you order one of these units from these people in the States, you've got two options. You can go for one which costs you around £40, which is calibrated to a specification of plus or minus 0.3060 volt on the output, or you could go to the same unit effectively that is being calibrated to a much higher spec to give you plus or minus 0.0002%. That's 2 parts per million, and that particular unit they charge you just over £60 for that particular unit, a little bit more than £60. The only thing you need to bear in mind is that these units come from the USA, and therefore there will be import duties to pay and delivery costs, so you need to add that factor in when you're ordering these items. I'll just quickly show you the eBay site for this particular IC. There you have the listing for the cheaper of the two modules that these people do, and as you can see there, the cost is $59.95. Well, I hope you found the teardown and review of these voltage reference modules of interest, and I'll see you all again next time. Bye for now.